All right. Good morning, folks. Welcome to our review session for our first exam for Math 122. So thank you so much for filling in all of the feedback in the Canvas discussion. It was really helpful to kind of see like what people wanted to go over. Um, I know some of you asked, oh, just give us a preview of the test. And I'm going to be telling you right now that we're not going to do questions that look exactly like the exam, but we will review the specific topics that people did address. All right. So for example, integration by parts definitely came up a lot. So we're going to start there and we will see what comes up next. All right. So we'll do a couple examples, we'll see what happens, and then we'll move along. Okay, so integration by parts is one of the first integration techniques that we looked at. And in particular, we had this idea that if we had our integral of u dv, that we could then find that to be uv minus the integral of v du, okay? And so with that formula, I think what was really important is that we were looking at sort of like one function, our u, and then another function, our dv, and they were being multiplied together. And so let's do an example of when we might see something like this. So let's say we had the integral of 2x e to the 9x, all right? So I can see here that I've got two different functions. I've got a 2x, I've got a e to the 9x, but what is really important here is that we see that they are multiplied together, right? And that's the secret operator that's between our u and our dv. And so this looks like a really good way to, or application of integration by parts. And I would encourage you to do this along with some that you know are U sub, some that you know are integration by partial fractions, and see if you can tell why we're using integration by parts, okay? I'm really going to want you to know how to make that decision. But as we review integration by parts, we had this idea of using the phrase late to help us figure out what was our u in this case, okay? So if there was any logs, then that came first as our u, but I don't see any logs, and so next up is our algebra. And I do see a 2x, and so what that means is my u is going to be my 2x, all right? And in particular, that's because I have an algebraic term here. What that means is my dv is going to be the rest of it, e to the 9x dx, all right? You got to make sure you write that dx. If you don't write the dx, it's not fully correct, okay? All right, from there, with our u, we take a derivative, du, and we get 2 dx. And then from our dv, we integrate to get our v. Now this requires some u substitution. And so if we kind of do that u substitution off to the side, all right, we're going to let u equal 9x and du will equal 9 dx. And that means that I really have 1/9 du equals dx, okay? And so when we integrate, we end up with 1/9 e to the 9x. All right, now we've got our setup. So we're going to plug everything into our uv minus the integral of v du formula. So I've got my integral. It's going to equal u times v. So that's 2x times 1/9 e to the 9x. That's u times v minus the integral of v times du, okay? Now, as far as algebraically simplifying things, I do expect that we're able to turn things into a single fraction. So for example, over here, it looks like I have 2x times a bunch of other stuff, but we can actually write this as a single fraction. And so one way that I find really helpful is to like put out a fraction line and think about what's in the numerator and what's in the denominator, okay? So in my denominator, I very clearly have a 9. And as it turns out, that's going to be the only thing in our denominator. Everything else, 2x and e to the 9x are all over 1, so they're in the numerator, right? 2x e to the 9x. Now, before I integrate the second part, what I want to do is take any constants that I have out and pull those out to the front. And so in particular, I have a 1/9 I can pull out to the front, and I have a 2. So I really have minus 2 over 9, the integral of e to the 9x dx. Okay, so I've got my constant out front. And now look at this, the integral of 9x dx. Well, we already did that when we were finding our v. Okay, so the integral of 9x dx is 1/9 x or e to the 9x, right? So we put that all together. We've got 2x e to the 9x over 9 minus 2/9 times 1/9 e to the 9x. And because we don't have bounds, we want to make sure we have a plus c. Okay, I'm going to take one last step and clean everything up. So I can take a 2 times a 1 to make my numerator. And e to the 9x is also going to be in the numerator. But 9 times 9 is going to be my denominator. And so altogether, I'll have 2x e to the 9x over 9 minus 2e to the 9x over 81 plus c. Okay, so there's our first example. We have an integration by parts, and that's basically how we do it. Okay, let's maybe try a slightly different flavor of this one, and then we'll pick a different question to take a look at. Okay. So let me add a page after. Great. All right. So let's try one more example. And I think, again, the idea here is I want you to practice your decision making. So like, how do you know that we need to use integration by parts versus any of the other techniques that we know? Okay. So we've got this one, the integral of the natural log of 11x over x to the 5th dx. Okay. So we'll take a look at this. I see two functions and they look to actually be divided. Okay. So let's think about this for a moment. If we go back to that idea of logs, algebra, trig, and exponentials, if we see a log, that is going to be our u, okay? And so what that means is that my u in this case is going to be natural log of 11x, okay? Now, while I'm here, I'm going to go ahead and find my du. So natural log, that will be 1 over 11x times 11 because I have to use the chain rule. Okay, so a lot of these questions do involve more than one rule. I see natural log of something that's not just x, so I have to use my chain rule. But let's clean this up for a moment, all right? This is really saying, oops, don't forget the dx. This du is really 11 over 11x dx, which we can simplify to 1 over x dx. Okay. Now, you might be wondering, well, why are we using integration by parts here when this clearly looks like a division? And maybe it would be helpful, I'm going to slide the late right over here. Maybe it would be helpful if we thought about this original problem like this. The natural log of 11x times x to the negative fifth dx. Okay. Now I can see that multiplication operator, which is a really good clue that we're going to do integration by parts. Okay. Now, if my u is natural log of 11x, that means the rest of this is my dv, okay? So dv equals x to the negative fifth dx. And when I integrate there, I'm going to add 1 to the power and divide by that power added 1. So in other words, I get x to the negative 5 plus 1 over negative 5 plus 1, which is x to the negative 4 over negative 4. Okay. So we've got our setup here, and just like the last question, we're going to go ahead and plug everything in to our formula. All right, so we've got u, so natural log of 11x, times v, so x to the negative 4 over negative 4, minus the integral of v times du. Okay. This is the calculus. At least this part is. We still have to integrate the second term, but we're going to simplify it just like we did in the first problem. Okay. All right, let's see what we got. Now I think we can do something similar over here where we can turn that into a single fraction. Okay. I'm going to go ahead and set up my fraction line. Think about what's on the numerator. I think this time it's just my natural log of 11x. Because this x to the negative 4 has a negative exponent, I can actually move that down to the bottom, and it'll stay with that negative 4. So negative 4x to the 4th. All right. Now let's simplify this integral to make sure that we can take the integral of the most simple term possible. And just like last time, I'm going to pull out the constants. So the negative 4 on the bottom and the 1 on the top are going to come out. So I get plus 1 over 4. The integral of x to the negative 4, I can write as 1 over x to the 4th. But that means I can actually write 1 over x as x to the negative 1. And so what I really have is x to the negative 4 times x to the negative 1, which if we do a little bit of algebra, we see that that becomes x to the negative 5. Okay, because we add our exponent. Now, the nice thing about this is we've already found the integral of x to the negative 5. It is x to the negative 4 over negative 4. So in some ways, we've already done the work for this second part, okay? So we get natural log of 11x over negative 4x to the 4th plus 1/4. Okay, what was that integral again? Ah, that's right. X to the negative 4 over negative 4. So times x. Ah. Okay. We're being a little fussy right now. All right, let me erase and try it again. Times x to the negative 4 over negative 4. That's not showing up, is it? Ah, there we go. Okay. That's our integral. Oh, come on now. All right, that's our integral, and we don't want to forget our plus c. Okay. Last thing, let's clean up our fraction, make sure we got a single term where we can. We get natural log of 11x over negative 4x to the fourth minus 1 over 16x to the fourth plus c. All right. And let me get that all on one page for you. All right, so here's a different example for our integration by parts. All right. Now, I know that you already did a homework assignment on this and you've already done your notes on this, but I would encourage you to go back to the notes. You have those answer keys, try them again, see how they go. And same thing with the homework, go back to them, try it again, see how they go. Okay. Definitely a case where like the more practice we do, I think the easier things will become. Okay. So integration by parts. I also saw a lot of people wanting to do our improper integrals. So let's kind of shift gears a little bit and try looking at some improper integrals. All right, we'll add a page. All right. So for improper integrals, we have the integrals where we have infinity in the bounds, okay? So let's take a look at an example. All right, so I've got an integral from 2 to infinity of 1 over x to the fourth dx, okay? Now, I want you to think for a moment, how do you know that this would be an improper integral, okay? And I hope that you're thinking, oh, because I have that infinity. All right. So that is your clue. Okay, if I have the infinity, I have to use the process that we learned in 11.1 about improper integrals. Okay. All right, so let's figure out whether this integral converges or diverges. So first thing I'm going to do, I'm going to swap out the upper bound for a number, and I'm just going to call that number b. All right, so I have the integral from 2 to b of x to the negative 4 dx. And in front, because I've changed this infinity to a b, I have to take the limit as b approaches infinity. This is the thing that will get me back to the original form at the end of the day. So if I don't write this, then everything else is wrong. Okay, you have to include this so that we know at the end we're actually pretending that b gets to infinity. Okay. The other thing I did here is I rewrote this so that I could see my power very clearly, so I can use my power rule, okay? So I would encourage you to do that. If you see things with powers on the bottom, I would encourage you to rewrite it so you can see that or to see that actual power. All right, once we have all that, we integrate and then we take our limit, okay? So we keep our limit as b approaches infinity, and now we integrate, right? So at this stage, we're going to integrate, and then after we integrate, then we're going to plug in b is going to infinity. All right, what is our integral? X to the negative 4 plus 1 over negative 4 plus 1. And I'm plugging in b, and I'm plugging in 2. Okay? So that's my integral stage. Whoops. All right. And now that I've integrated, let's simplify before we plug in our bounds. Okay, so I still have the limit as b approaches infinity. I didn't use it yet, so I have to keep it there. But the thing that I'm integrating is x to the -3 over -3 from b to 2. And let's take one more step where we put this x to the -3 on the bottom, so it'll be a little bit easier for us to plug in our bound. Right? The limit as b approaches infinity of 1 over -3x to the third. And I'm going to plug in b, and I'm going to plug in 2. All right, let's bring this over here. Now I'm going to go ahead and still have my limit as b approaches infinity of -1 over 3b cubed minus -1 over 3 times 2 cubed. Okay, so all I'm doing is I'm plugging in my b in the first integral, and I'm plugging in my bottom bound 2 into the second one, and then I subtract them. All right, let's plug in our infinity for b, and let's simplify this second fraction. Okay, so we get the limit as b approaches infinity. Oh, no, we're plugging in infinity, so I don't need this part anymore. So -1 over 3 times infinity cubed plus 1 over, okay, let's be really careful here. We need to cube it first. So 2 to the third is 8. 8 times 3 is 24. Okay. Now this is the part where we have to think about what happens when we plug in our number. All right. And if we remember from the lecture, and again, if you don't remember, that's okay, but I would go back and watch that part again. This is really saying 1 over a really, really big number, which mathematically is the same as saying 0. Okay, so we take one thing, we cut it up into an infinite number of pieces. Each number or each piece is just going to be 0 in size. It's going to be really, really small. That means we have 0 plus 1 over 24, which is just 1 over 24. Okay. So let's look at this whole question on one page for a moment. I did my improper integral, I integrated, and then I took my limit. That's what's happening down here. And after I took my limit, I got a number. I'm going to leave it to you. Go back to the video and you tell yourself, I got a number. Does that mean that my integral converges? Or does it mean that my integral diverges? Okay. So which one is it? Go back to that 11.1 video and I bet you'll find it in there what that does. All right. So I'll get that equation for you all on one page. All right. And let's pick another problem. Okay, let's get a new page. Okay. So let's say that I am going from -infinity to 4. Okay, so let's make the bottom bound the -infinity this time. Same idea. I don't even need to see the rest of the question, but I know with that -infinity, it means I'm going to follow the same process as I had on the other page. Okay. All right, let's make up a function. Let's say 1 over 50 square root of x dx. Okay. All right. We want to write this as the integral from a to 4. Okay. So we're choosing some number a, 1 over 50 square root of x dx. And ultimately, at the end, we're going to take the limit as a approaches negative infinity, right? And this limit part is what will get the bottom number back to negative infinity. Okay. Now, kind of like in the last example, how I rewrote that 1 over x to the 4th as x to the negative 4, I'm going to rewrite this with some algebra so it might be a little bit easier to integrate. Okay. So we've got the limit as a approaches negative infinity of the integral from a to 4. And I'm going to take that 1 over 50 and I'm going to move it out to the front. Okay, so the 1 over 50 is a constant, so I can move that out to the front. And then this square root of x on the bottom is the same as x to the negative 1/2. Okay. And so now when we write it this way, I think we can see that when we integrate, we're going to need to use our power rule. All right. So it looks kind of complicated in the beginning, but ultimately when we rewrite it, it's just going to be power rule. So we've got 1 over 50, the limit as a approaches negative infinity. All right, integral time, x to the negative 1/2 minus 1 over negative 1/2 minus 1. I'm plugging in a 4 and I'm plugging in an a. All right, let's definitely clean this up before we plug in our values. 1 over 50 times the limit of a approaching negative infinity of, okay, this is x to the negative 3/2. Okay, and this on the bottom is negative 3/2. So I end up with 1 over x to the 3/2. Okay, that's that negative 3/2 power, we move it down. And then if I'm dividing by negative 3/2, that is the same as multiplying by the reciprocal. So it's the same as multiplying by negative 2 over 3. And I'm going to plug in 4, and I'm going to plug in a. Okay. So let's clean this up a little bit more, and then we're going to go ahead and plug in our bounds. So 1 over 50, the limit as a approaches negative infinity of negative 2 over 3 times the square root of x cubed. We're going to plug in 4, and we're going to plug in a. All right. We've got 1 over 50. The limit as a approaches negative infinity of negative 2 over 3 times the square root of 4 cubed. So I plug in my top bound first, minus the negative 2 over 3 times the square root of a cubed. Okay. So I'm plugging in my top bound first, and then I'm plugging in my bottom bound second, and then I subtract the 2. All right. From here, let's go ahead and clean up some things and go ahead and plug in negative infinity for our a. Okay. 1 over 50, we get negative 2 over 3 times 4 cubed plus 2 over 3 negative infinity cubed. Okay. Now we're dividing by infinity. All right, the same idea. And when I divide by infinity, I'm essentially going to 0. And so what I have left is this gross looking thing, 1 over 50 times negative 2 over 3, the square root of 4 cubed. And this is our gross looking but correct answer. Okay. So we follow the same process. It just depends which one we swap out for A or B, right? If it's the bottom bound, we swap out for A. If it's the top bound, we swap out for B. And we work through them. And at the end, we'll either get a number or we're going to get infinity. And again, I think what I want you to go back and just check that 11.1 video is, does that mean that our integral converges or diverges? Okay, but I promise you that's in the video there, so I'll leave that for you. But let's get this all on one page so we can take a look at our improper integral. All right. It also seems like people are interested in the partial fractions. So let's take a look at some of those partial fractions questions. All right. So, okay. Let's actually take a look at question number 4 from the homework, right? What I like about question number 4 from the homework is that it involves a lot of factoring. And so that is one thing we might want to make sure we know how to do for exam days. We want to know how to factor, okay? So we'll do our partial fraction practice. Okay, so here's our example. We have the integral of x squared plus 4 over 3x squared plus 4x minus 4 dx. Okay. So one thing I might notice here is like this kind of looks like our second example, I think, right? Where, let's go back a little bit, where we kind of had things that were divided by each other. But the difference here is when I see two different kinds of functions, like a log and a polynomial, or like an e, like we had in this one, an e and a polynomial. When I'm mixing and matching function types, that is a pretty good indicator we want to use integration by parts, okay? But when I go back to this partial fraction business, I notice that everything is a polynomial, okay? So because everything's a polynomial, that's a good indicator that we should try partial fractions. All right. Now, partial fractions means at some point I got to break this down into like, oh wait, this is x cubed, squared, and x. All right, so I have to break this down into like a fraction plus another fraction plus another fraction. And I'm not really sure how many I have, but once I factor the denominator, that will tell me how many fractions I need. So let's factor, right? So 3x cubed plus 4x squared minus 4x. Now, let's take a look. I can take an x out of every single term. So that leaves me with x times 3x squared plus 4x minus 4. Okay. Now this one, I can factor using the factoring by grouping technique. Now I'm going to talk through it here, but if you haven't watched the partial fractions video, I definitely talk about it in there, and I've included other resources on how to factor, okay? So it's okay if you don't feel great about it now, but between now and next week, it's on you to figure out how to be better at it, okay? All right, so factoring by grouping, I'm going to take the 4 and put it up top, and then 3 times -4 goes on the bottom as -12. Now I want to find two numbers that add to make 4, but multiply to make -12. All right, I think -2 and +6, that's going to do the trick for us. So what that means is we've got x times 3x squared minus 2x plus 6x minus 4. All right, now we're going to split it in half, and we're going to factor by grouping in the first half and in the second half. All right. So this equals x times x 3x minus 2 plus, I can take a 2 out of here, so 2, 3x minus 2. Now this is a really good thing for us because 3x minus 2 is in both terms. And so I can factor this as x times 3x minus 2 times x plus 2. Okay, and that's the x plus 2 that go right there. Now, because I have 3 factors, I need 3 fractions here. Let me shrink this so I can leave myself a little bit more space. So that means I'm going to end up with a over x plus b over 3x minus 2 plus c over x plus 2. Okay. Now, this is an assignment. This is the one assignment where I collected homework from people. Make sure you show your work, okay? And this is true for all questions. I'm not giving credit for magical answers, so I need to be able to follow the work that you show to get to the right answer, okay? All right, so let's see what we get. All right, now this is where we need to create an equation, right? We need to make sure the denominators match on both sides, and then we can set the numerators equal to each other. So that is going to require a lot of space. So I'm actually going to start here so I can actually write all the way across the page, okay? All right, so we have x squared plus 4. That's the numerator on the left-hand side, equals a, and now I have to multiply a by the other 2 denominators. So a times 3x minus 2 times x plus 2. Plus b, I have to multiply by the first and the last denominator. So plus b times x plus 2. Plus c times the first 2 denominators multiplied together. So plus c times x times 3x minus 2. Okay. Now, there's a lot of ways to do this, but if you watch the videos that I had posted, my suggestion was that you choose a clever number. Okay, if you choose a clever number for x, it should be able that we are able to find a, b, and c pretty easily. Okay, we just have to make sure our signs are good, that we've added correctly, but it's not too bad. So let's let a equal, or x equal 0. Let's start from there, okay? That means in this whole long equations, both sides, everywhere there's an x, I'm going to plug in 0. Okay, so 0 squared plus 4 gives me 4. Equals, let me plug in a 0 here. So I get a times 3 times 0 minus 2 times 0 plus 2. Okay, plus, look at what I'm going to have here. B times 0. So b times 0, 0 plus 2, plus c times 0 times 3 times 0 minus 2. And the lovely thing about this is going to go to 0, and this is going to go to 0. So by cleverly choosing that number, we end up with only a as something we don't know in here. All right, let's find a. 4 equals a times negative 2 times 2, which means 4 equals negative 4a, and a equals negative 1. Okay, so we've got our a value. Now let's think about a clever number to choose to find b and to find c. Okay, now I think a really good thing to do would be to pause this video right here, just so you could practice finding those numbers and seeing what you get. All right. But for right now, let's keep moving. All right. Now I'm going to plug in x is negative 2 and kind of see what happens from there. And I have to plug it in everywhere, which means I have to plug it in on the left side too. So negative 2 squared plus 4 equals, all right, if I plug in negative 2, my a term is going to go away. And if I plug negative 2 in for x here, the b term is going to go away. So really the only thing I'll have left is the c. So c times negative 2 times 3 times negative 2 minus 2. And this gives us 4 plus 4 is 8. And then what does this give us? Negative 6 minus 2 is negative 8. And so I end up with 16c, or c equals 0.5. Okay. So it's okay if you want to use a fraction or a decimal there, but you could also leave it as a fraction if you like. All right, let's choose our last value. I hope we are thinking that x will be 2/3. Because when I plug in 2/3 for x, that's going to make some of the other letters go away. Okay. Now it's okay for things to be as fractions, all right? Again, on the exam, I will probably use very nice numbers. We won't have like 2/3, it'll be more like 1/2. But I want us to be able to work with fractions at the end of the day, okay? So I'm going to plug in the 2/3 squared plus 4 equals, okay, the a term is going to go away because 3x minus 2 is going to go to 0. And my c term is going to go away for the same reason. The only thing I need to plug in here is for b. So b times 2/3 times 2/3 plus 2. All right, so I get 4/9 plus, I'm going to turn 4 into 36/9 equals b times 2/3 times 2/3 plus, I'm going to turn the 2 into 6/3. Okay. All right, let's do some fraction work. We end up with 40/9, which equals b times 2/3 times 8/3. And I get 40/9 equals 16/9b. And that means that b is 2.5. Okay. One word of advice, don't take 2/3 and round it to 0.6. If you round it to 0.6, you're going to get a weird number at the end because you rounded. okay? So if it's a fraction, keep it a fraction as long as possible so you don't get the wrong number at the end of the day. All right, let's shrink all this algebra work here. Important work, but we want to make sure we leave room to answer the question that we have, which is actually our integral. Okay. So what do we have? We have the integral from a, which is -1 over x, plus b, 2.5 over 3x minus 2, plus c, which is 0.5 over the last factor, which is x plus 2. Okay. Now, I think what makes these kinds of questions hard is you have to know your factoring. If you don't know how to factor, and if you mess up your signs a lot, you got to take the time to double check on test day, okay? But I promise you, the more you practice these, the better it'll be. All right, so now let's integrate. And this is where I saw a lot of people skipping steps on the homework, and that's not really going to be acceptable on test day. So I really want to show you what I'm looking for you to write, okay? When I do this second integral, I need to do u sub. So I need to see you write out that you're going to do u sub, okay? So u equals 3x minus 2, du is 3 dx, and we're dividing the 1/3 over to the other side. Got to show that work. No magical answers, okay? Same thing for this third fraction, you got to use u substitution. Our u is going to be x plus 2. Our du is dx, right? And now, let's see, actually, we did like a u1 before, right? And this will be u2. Now we can go ahead and integrate, okay? So we end up with -1 over x dx. That's my first integral, and that one we don't need u sub for, okay? Plus 2.5 over 3, the integral of 1 over u1 du1, plus 0.5, the integral of 1 over u2 du2. Okay, so only at this point can you actually integrate, right? So you've got to show me that u sub if you need it. All right, let's integrate. We get negative natural log of, you have to use the absolute value, okay? No absolute value, it's not right. Plus 2.5 over 3 natural log of u1 plus 0.5 natural log of u2. Don't forget the plus c. All right, let's plug back in our u1, let's plug back in our u2, and then we'll have our final answer. So negative natural log of the absolute value of x plus 2.5 over 3, the natural log of 3x minus 2, plus 0.5 natural log of x plus 2 plus c. All right. I don't want you to combine your logs. Leave it like this. Leave your logs like this, okay? Too often I find when students combine them, they don't really do it right. And if they don't do it right, I can't give you credit for it, okay? So get up to this step. Don't worry about anything else. You've already done enough work, okay? So let's get that partial fraction decomposition on one page for you, but hopefully this is a helpful reminder on how to do that partial fraction decomposition. All right. Right. So it looks like some people also had questions on our, where did it go? On the trapezoidal and the Simpsons. So let's take a quick look at that. All right, so we'll add a page. So trapezoid and Simpsons approximation. Whoops. All right. So in the video for this one, I had talked about sort of like what it is that we're finding and shown some pictures there. That would probably be good to look back on, okay? But let's think about what we might do in terms of a question, okay? So let's start with an example. We've got an integral from 1 to 7 of the square root of 4 plus x to the 4th dx, okay? You've got an integral, and I want us to use Simpson's and trapezoidal rule to approximate this. So give me a second. I'm going to grab my calculator, if I can find it. What kind of math teacher doesn't know where her calculator is? I'm not really sure. Okay, so we got a calculator, all right? And let's think about what our formulas are and also like how we figure out how to set up our tables, okay? So let's start with the trapezoidal. Let's say that I want you to cut this up into, let's see, 3 sub-intervals. What that means is I want 3 trapezoids, okay? So it's really important that we look at the number here that tells you how many sub-intervals, and then the T will tell you you're using trapezoidal, but if I had an S, that means that you're using Simpson, okay? Now, if we look back at the notes from 11 or from our 6.4, okay? I kind of break it down into like 3 different steps on how we find this. So our first step here, okay? My first suggestion was to draw the interval and then cut it into as many pieces as we need so that they are like exactly split up evenly, okay? So in this case, on my number line, I want to go from 1 to 7. So from 1 to 7. And I can even think like this. This is 2, 3, 4, 5, 6. Okay. Now, if I want to cut this into 3 even pieces, if I split it like this, I'm going to get 1, 2, 3, right? And each of those have a delta x of 2. So from 1 to 3 is 2. From 3 to 5 is 2. And from 5 to 7 is 2, okay? So what this means is that my delta x equals 2. But for some of us who like a formula, another way you can think about that is you can do b minus a over m. Now, what do I mean by that? I mean b, which is 7, a, which is 1, and n, which is 3. So 7 minus 1 over 3, that gives me 6 over 3, which is exactly the same as if I draw a number line and cut it into even number pieces, okay? So I would pick one of these methods. If you like the number line, use the number line to find delta x. But if you don't like the number line, you prefer a formula, then use that formula, okay? All right. So after we found our delta x, then in the notes, I was like, let's create a table. Okay, so that'll be our next step. And our table will have x and f of x values. And let's see, what color highlighter did I not use yet? Green. The f of x is the thing that you're integrating. So in this case, our f of x is the square root of 4 plus x to the 4th. Okay? Now, the values I'm going to use for x, this is where it's important that we choose carefully. We do the start, and then the ones that we split in the middle, and then the end. So in this case, I should have 4 x values, okay? 1, 3, 5, and 7, right? Now, I will tell you how much you should round to, but it's going to be like our homeworks. You're going to round to 4 decimal places in here, and then at the very end, then you round to 2, okay? So first, we're going to take 1 and we're going to plug it into our function. So I get the square root of 4 plus 1 to the 4th. And that gets me a decimal of 2.2361. Okay, I'm going to do the same thing with 3. Square root of 4 plus 3 to the 4th. And that gets me 9.2195. And do the same thing with 5. Square root of 4 plus 5 to the 4th. And that gets me 25.0799. And I'm going to do the same thing with 7. Square root of 4 plus 7 to the 4th gives me 49.0408. Okay. We've made our table. And now we're going to go ahead and plug everything into our formula. And our formula says T sub 3 is going to equal f of 1. So 1 copy of the first one plus 2 copies of the second y value plus 2 copies of the third y value plus 1 copy of the last y value times our delta x, which is 2, and then divided by 2. Okay, so remember, for trapezoid, we divide by 2. For Simpsons, we're going to divide by a different number. Okay, so we plug in all of our values. Let's see what we get here. 2.2361 plus 2 times 9.2195 plus 2 times 25.0799 plus 1 times 49.0408. Okay, that gives me all the y values of 119.8757. And then I know that 2 divided by 2 is 1, so I'm really multiplying by 1. And at the end of the day, I'm going to chop off. I'm going to round to 2 decimal places, so I'll get 119.88 as my approximate area underneath this curve. Okay, so that's doing trapezoidal rule, but let's do the same problem using Simpson's rule and see how that might be a little bit different. Okay, so I'm going to go ahead and grab this and we'll copy this. And we'll paste it on a new page. Okay. And this time, our question will be asking you to find S of 3. Okay. So I know that our notation is a little bit different here. So let's be clear here. When we have our Simpsons, the number down here is really 2n. Okay. So if my n in the trapezoidal is 3, that means 2n for Simpsons would actually be 6. Okay, so whatever your n value is, you have to double it for Simpsons, but you keep it that way for trapezoidal. Okay, so what that means for us is S of 2 times 3, or we're going to find 6 divisions here. And all of the divisions at the top, because we're using Simpsons, will be like rounded little parabolas. Okay. Now, the nice thing is we follow all of the same steps, except our formula is different. Okay. So step number 1, let's go ahead and draw our number line again and find our delta x. 1, 2, 3, 4, 5, 6. And now this time, I think we can see if we want to split this into 6 pieces, each piece will just be 1 wide. Okay. Now what that means is our delta x equals 1. But again, we can use that same formula we used last time to help if we don't like cutting it up on a number line. We can say b minus a over 2n, right? So b minus a over 2n gives us 7 minus 1 over 6. We get 6 over 6, which equals 1, which is the same thing we got using our number line, okay? So choose a method that works for you. Doesn't really matter which one, but it just matters that it works for you. Okay. Now I'm going to need to make a pretty long table over here. So let me resize this. And we'll move this over. Great. Okay. So let's get an XY table. And we'll have our x and our f of x. Okay. Now this time I want to use all the divisions and the first and last value. So I'm going to use 1, 2, 3, 4, 5, 6, and 7. Okay. So my x values going to be 1, 2, 3, 4, 5, 6. Oh, I didn't plan very well. We'll squeeze 7 down here. Okay. Now on a test, I would like you to write out your table, because what happens if you type in a number wrong, right? If you just give me your final answer, I have no idea where you went wrong. But if you show me your work on the table and I'm like, oh, they just typed in this one number wrong, I can at least give you partial credit. Okay. And I want to give you partial credit. So help me help you. All right. We're going to plug all of our x values into our 4 plus x to the 4th under a square root. Now, some of these values I have from my previous problem, right? So I know that for 7, the y value is 49.0408. I know for the 5 value, it is 25.0799. I know for the 3 value, it's 9.2195. And I know for the 1 value, I have 2.2361. Okay, so really, I just need to find the 2, the 4, and the 6 y value. So let me go ahead and do that. The square root of 4 plus 2 to the 4th. That gives me 4.4721. Okay, now I'm going to plug in 4. Square root of 4 plus 4 to the 4th is going to give me 16.1245. And now I'm going to plug in 6. So square root of 4 plus 6 to the 4th, and that's going to give me 36.0555. Okay. So I've got all of my y values now. Now I need to plug them into the formula. So if I plug it into this formula that I used for the trapezoid, well, that's going to be wrong because that's for the trapezoid approximation. So I want to make sure I use the correct formula, which is our Simpson's approximation. Okay. So the Simpson's approximation means that we have one copy of the first y value plus, this is where it starts to get a little different, 4 copies of the second plus 2 copies of the third plus 4 copies of the fourth plus 2 copies of the fifth, ooh, plus 4 copies of the sixth, also bad spacing, sorry, plus 1 copy of the seventh. Okay? So instead of saying 1, 1, and then just like 2, 2, 2, 2, 2 all the way across, I'm alternating, right? 4, 2, 4, 2, 4. All right, now we got to do times our delta x, which is 1. And this time we are not dividing by 2, we're dividing by 3. Okay? All right, let's plug this all in. Let's see what we get. 2.2361 plus 4 times 4721, 0.4721 plus 2 times 9.2195 plus 4 times 16.1245 plus 2 times 25.0799 plus 4 times 36.0555 plus, we're at the last y value, so only one copy, 49.0408. That gives me 346.4841, and I'm going to divide it by 3. And I end up with 115.4947. I want to round to 2 decimals, so I get 115.49 as my approximation. Okay? All right. So we've got our Simpsons, we've got a trapezoidal. It's really about knowing the formula and what you have in terms of finding your n value. Okay? All right. Let me pull up my announcement from last week real quick. All right. So a couple of reminders here before we sign off. So reminder number 1, you have a learning portfolio that is due. All right. So please make sure you do that learning portfolio. There's sort of a part A and a part B, like one before the test and one after the test. Okay. Exam 1, I would encourage you to start making your reference sheet right now. Okay. So I'll talk more about that in the La Semana, but then after your exam, it would be important to make sure you can come back to campus and pick up your exam so that you can do your learning portfolio part B. Okay, but I'll put together a week La Semana for that later on this week as reminders on how to prepare for the test. Okay, so I'm going to stop the recording here.